A differential manometer is connected at the 2 points A and B as shown in figure. At B, air pressure is 9.81 Newton per centimeter square absolute. Find the absolute pressure at A. So this is the given diagram, that is it is a U-tube manometer which is connected two vessels, one is A and another one is B. Here vessel A is connected this side and vessel B connected on right side. Okay, see here vessel A consists a fluid of specific gravity 0.9 and vessel B consists it is a water of specific gravity obviously 1, and in between the fluid of specific gravity 0.9 and water there is a mercury which has specific gravity of 13.6. Here datum heads are given, that is 60 centimeter of water as well as 10 centimeter of mercury and 20 centimeter of fluid which is having specific gravity 0.9. Here the options are A 2.2 Newton per centimeter square, B 4.4 Newton per centimeter square, C 8.8 Newton per centimeter square, D 9.45 Newton per centimeter square. Coming to the solution, so here we will have to apply Pascal's law, which is stated that any 2 points at the same elevation in a continuous mass of the same static fluid will be at the same pressure. That is, here consider mercury at the same points in two columns and consider as the datum line XX. Here we have a XX line which shows the mercury at two levels and in two columns which are in same position. So here at the 2 points pressure is same, and by applying Pascal's law here again, which is given by Pa plus rho gh of a fluid, let us say 1 plus rho gh mercury, and which is equal to pressure at B plus rho gh of water, that is let us say H2O. Okay, here we'll have to find out pressure at the A. So but we know that rho gh1 represents here H1 represents here the fluid head of specific gravity 0.9 which is the head of, let us say it is again plus head of 20 centimeter which is given by 0.2 meters into where rho g is the 9.81 into 900, where rho is the specific gravity into the density of standard fluid, that is water, so which is equal to 900 plus here comes to the mercury density is given by 13,600 into G is 9.81 again, and the head of mercury is 10 centimeter, that is let us say 0.1 meter, and which is equal to here Pb is given by, what is the value of Pb here, 9.81 Newton per centimeter square. So let us write it in terms of Newton per meter square, that is 98100, 98,100 Newton per meter square plus, and we have a head of water head of 60 centimeters, so which is given by 1 into 0.6, 1000 into 9.81 into 0.6. So here is the total pressure distribution across the U column. So by using this equation we can find out the pressure at A and is equal to 88619 Newton per meter square, and also we can write it as 8.86 Newton per centimeter square. So here the correct option is C and is given by 8.88 Newton per centimeter square. two pipes each 300 meter long available for connecting to a reservoir from which a flow of 0.085 meter cube per second is required. If the diameter of the two pipes are 0.3 meter and 0.15 meter respectively, determine the ratio of head loss when the pipes are connected in series to the head loss when the pipes are connected in parallel and neglect the minor losses. Options are 35.7, 45.7, 55.7 and 66.6. Here, when the pipes are connected in series, then the head loss due to the friction is equal to sum of the head loss due to the friction in the pipe 1 and head loss due to the friction in the pipe 2. And we can write it as the head loss due to the friction is equal to HF1 plus HF2, that is the head loss in pipe 1 plus head loss in pipe 2, and which is given by FL V1 square by 2GD 1 plus FL VT square by 2GD 2. And here we can write it as Q is equal to velocity into area, that is given by, we can modify here V1 square by D1 into FL Q1 square by 2G into pi by 4 whole square into D1 power of 5. That is, here we are converting V1 in terms of Q and area plus FL Q2 square by 2G into pi by 4 whole square D2 power of 5. Here Q1 is equal to Q2 because the pipes are connected in series, so that here Q1 is equal to Q2, and which is equal to 0.085 meter cube per second. And we know that here diameter of the pipes, here diameter of the pipe 1 is 0.3 meter and diameter of the pipe 2 is 0.15 meter. On the substitution of all the values, we get here 98.12 into FL by 2G into pi by 4 whole square. So this is the head loss in the pipes when they are connected in series. Now consider head loss due to the friction when the pipes are connected in parallel. In case of pipes are connected in parallel, let us say Q1 and Q2 be the discharge in the bigger and smaller pipes, so that the total flow is equal to sum of the Q1 and Q2. Let us say this is H of series, and here the head loss due to the friction when they are connected in parallel is given by either head loss due to the friction in the pipe 1 or head loss due to the friction in the pipe 2 in case of parallel case, and the total discharge is equal to Q1 plus Q2. And HF1 or HF2 is given by FL Q1 square by 2G pi by 4 whole square D1 power of 5, or which is equal to FL Q2 square by 2G into pi by 4 D2 power of 5. Here pi by 4 whole square into D2 power of 5, and here which is equal to, here we can get HF parallel is 2.147 into FL by 2 into pi by 4 whole square. Sorry, here 2G into pi by 4 whole square. Therefore, the ratio, that is head loss due to the friction when pipes are connected in series to head loss due to the friction when the pipes are connected in parallel is equal to 45.7. So in the option, it is the correct option is B, that is 45.7.